box on bottom would balloon up and become quite large, and it would become large very quickly. So the zooplankton are keeping this small box, in fact, very small. So it's just the simple fact that, like, in every given instant, you are producing, like, one phytoplankton is becoming two phytoplankton. Now you're not ballooning up and becoming like, because if you're doing that type of a, like, basically like binary fission or cloning event, then this box on bottom would become huge quickly. But however, the zooplankton are keeping it in check. So again, the reason you don't see this on, you're like, well, why don't we do that on land? Well, because if you think about it on land, you could recognize that, like, the growing of hay or of a tree is something that takes you years worth of time. The turnover time, the generation time is quite long. So hence you would need a larger producer level on land than you would in the water, where production can happen or production growth can happen very quickly. Yes, sir.
So is the mass basically the mass of that organism in the environment? Oh, okay.
Like, this is the mass of all. Like, if I cut down every single like stalk of hay on Dad's ranch, that would be the producer biomass.
Okay.
If this was the cow level, this would be taking all the cows and putting them on a scale, massing them all. It's not for one single cow; it's for every cow that's on the ranch. Cool. Or in that system. We've talked about a lot of different biochemical cycles or biogeochemical cycles. I think most of these are pretty much set in your mind because either one, we've talked about them. So we've either talked about these or you can figure them out real quickly. I'm going to write down the cycles that you need to know. If you think that you need to review these, then I would say go for it. The water cycle. I don't think you have to review that because I think you know what rain is and all that other kind of stuff. So that's probably, yeah, I know. But like I think that's fine. We've talked about nitrogen cycle. Who is like primarily responsible for manipulating the nitrogen cycle? Do it? Bacteria. Okay. Carbon cycle. Plants and respiratory creatures. One cycle you might not be super familiar with is phosphorus. If you want the simple piece on phosphorus, basically every creature has phosphorus in it. When they die, the little bacteria take the phosphorus inside the body, convert it to phosphate, a usable form by plants. And plants take up that phosphate, they use it for their own stuff, and round and round we go. A lot like a nitrogen cycle, except there's no phosphorus free floating in the air that has to be fixed. Just phosphorus from dead stuff that has to be fixed. We could talk about, some major issues that involve some global problems that we are concerned about today in ecosystems. We could talk about acid rain, overpopulation, greenhouse gases, certainly maybe the greenhouse effect. I think you should be familiar with him. Now, we've already talked about acid rain, how that is a negative, right? Remember what acid rain does is acid rain basically replicates cation exchange. So you basically delimit the amount of good minerals that a plant gets, which means that it grows up unhealthy and then therefore unedible. Overpopulation, we talked about how every creature is going to approach its carrying capacity and how, like, our carrying capacity is so much different because our resource that we use for that is not a sustainable resource. So how our carrying capacity is like way jacked up is compared to everything else. Greenhouse effect, believe it or not, I guess that's your call. Now, I can say that the ozone has been depleted, not because of necessarily greenhouse gases, but because of the use of something called CFCs, or chlorofluorocarbons. What these chemicals are is that they were used very heavily from about like the 1940s to the 1970s or 80s in canisters of hairspray or in Freon, which were used in cars and in refrigerators and stuff like that. And what these chemicals have done is they have literally chipped away at the ozone layer. So if you look at a picture of like Antarctica, you see that there's like basically this big hole where the ozone used to be at that point. What that's allowing to have happen is that's allowing an event in which like stronger rays from the sun are able to come in and possibly melt down some of your Antarctica landmass. Now, again, people are like, well, isn't that a greenhouse effect? And it's actually not, because greenhouse effect really deals with the carbon dioxide count and how much carbon dioxide changes over the course of time. What greenhouse effect says, if you think about what a greenhouse is a greenhouse is something that lets light in, but then keeps a lot of that energy on the inside. You walk into a greenhouse, it's always very, very warm. So the greenhouse effect is about how the carbon dioxide prevents sunlight from bouncing back off this planet, and how you have all this energy stay inside. The ozone depletion from chlorofluorocarbons is a totally different thing. They're related in some degrees, but they are different. And no one can deny that the ozone is being depleted by some of these chemicals we put up there. And a greenhouse effect is, again, a totally different thing. That is a debate if the carbon cycle is off or not. But I think you should be familiar with global problems and be ready to read like a little short bit about them. Now, if you want to jot this next part down, I'll go over like what your test is going to be over. You had the first chapter, which was about chapter 50. That was about just ecosystem ecology from a general perspective. And it's a really good intro chapter because it kind of shows you what chapters 52, 53, and 54 are going to be all about. I wouldn't suggest you read chapter 50. I would suggest, though, if you don't understand what a savanna is, or what the desert is, or what the tundra is, you look at the end of chapter 50 to help you understand what these different environments at least look like. So if you see it in a sentence, you can recognize that the tundra is going to be a very, very, very frozen, cold landmass. Cool. I think the other thing that you have to know, let's see, going into chapter 51, we talked about animal behavior. Chapter 51 is a pretty simple little read. You can read it or not. It's good reading for the explanation and for the examples that you have. However, it's not a requirement to read, I think. Really, on chapter 51, you really have to just focus on the vocab. Know the difference between trial and error learning, what habituation is, what operant versus classical conditionings are, things of that nature. For chapter 52, that's probably the pivotal chapter of this. If you haven't read 52 yet, I would suspect you're extremely behind. You definitely need to be reading 52. There's going to be things that I ask you from chapter 52 that we didn't have time to go over class and are from the book exclusively. So you will find on chapter 52 those questions. Like if you have this idea that, well, Mr. Fields, you didn't go over that. I realize that. There's not enough time to go over all of 52. That's why I suggested that you read it initially. If you've already read it once, good. Might suggest you read it twice. If you've already read it 2 or 3 times, then you probably are fine. But definitely 52. You should have already read. I suspect if you haven't read it by now, you either one are going to have a very long night, or two, you will fail this exam tomorrow. There's going to be a lot of questions topics I didn't go over. You got to read 52. In 52, the major things: R versus K selection. What is carrying capacity? What factors affect population growth? What factors affect population decline? Logistic versus exponential growth curves. Understanding the life tables. How we can determine a death rate. Type 1 versus type 2 versus type 3 organisms. What the implications of type 1 through type 3 are. And what density independent versus density dependent selection models are. So all that stuff right there on chapter 52. Tons of stuff. Good examples in the book. You're not talking about tons of reading, but definitely you want to be looking at it. Next is chapter 53, which is about community ecology. We talked about this a little bit on Friday, and we talked about it a little bit today. With community ecology, I think you want to know the difference between your interspecific interactions and your symbiosis relationships, your symbiotic relationships. Realize that predation is not symbiotic, and parasitism is not an interspecific interaction. There you want to see that there's a difference between those two things, and we did a really good job in class about that. Interspecific versus a symbiotic relationship. Know the difference between dominant, invasive, and keystone species. Understand top-down and bottom-top control mechanisms. Trophic levels, food chains, and food webs are all fair game as well from community interactions. From chapter 54, which is about ecosystem ecology, I think you want to be concerned about some of the topics we talked about today, which would include the global problems I mentioned up there, the biogeochemical cycles, trophic level design, and how you always have producers on the bottom and then you go up to consumers on the top. Then understanding what biomass pyramids are, what biomass itself represents, what is biomass as a topic. Understanding how aquatic ecosystems can have an inversion and how they can have that inversion. Nicole had asked for clarification on that a while ago, and that was because you can have so many phytoplankton produced in such a short amount of time, where you can't do that with trees on land or grass on land. So I think that that's fine. If I was going to encourage you to read any part of this,